Hello and welcome to another TSLOPE video. In this video, I will be showing how to import data directly from QGIS into TSLOPE. So as you can see, I have a QGIS project open. I've just shown you the material properties, and these will be what we're putting in as the geological units in the TSLOPE project. And on top of that, I have a boundary line, cross-section, drill holes. I've got some property tile data. And I have a base map, and that was the LiDAR data you just saw flashing up. And here I also have some point clouds which represent the different surfaces. So if we jump across to TSLOPE now, to access this database, I'm going to right click on the QGIS project folder and navigate to it. Here it gives me the option to add surface. I'm going to uncheck that box because I have the LiDAR and that is what we'll use as the top surface. So here, if I navigate to elevation and I right click and go to top, this is bringing the elevation LiDAR in as the top surface. It's a very detailed surface, which is why I'm getting this warning message. And it gives me the option to add the OpenStreetMaps geoimage. So I'll click yes to that. And here you have the image on top for context. Now, if I go down to my surfaces, I'll bring these up as the layers and as the phreatic surface. So this top of sand is going to be a layer. It's going to denote the start of the uncemented sand layer. And the base of sand is going to be the layer indicating where it transfers back into the different geological unit. And here the measured piezo is going to come up as our phreatic surface and measuring the water table. So now I have these surfaces loaded. I'm just going to change the colors to make it a bit more noticeable. Make sure like the phreatic surface is a blue, which it already is. I'll just change the color slightly. And these layers, make them a bit different so that we can see the difference in these layers. So now I've changed the colors, I'm going to add in the material properties. So I'm starting with this Waimata group, and I'm going to change the saturated and unsaturated values to match what the material properties are. I'm using Mohr-Coulomb as my failure criterion, but there are a few other failure criterions you can use. I'll change the cohesion and angle of friction, and I'll also change the color to give it a different appearance. Now I'm going to add a new material, and this is going to be the uncemented sand layer. And here I'm just going to change the cohesion to 0 and the angle of friction to 20 because this is what the material properties are. And I'll change the color so it looks different to the other material. So with those materials added, I can go ahead and move on to importing the other relevant information from my QGIS file. So I'm going to import across the boundary line, and if I right click, it comes up with this panel and the software automatically detects what kind of item this is. So you see I imported the cross-section line as well, and it noticed it was cross-section. Drill holes, it marks it and copies it to the drill holes. And the only other few things that I want to bring across are these property titles, just as annotations, so we have them in TSLOPE. And that should be about it. So if we scroll back up to the layers, I didn't do this previously, but I can do it now. I'm going to change the material for the top of sand to the uncemented sand and check that the base of sand is then going back to the Waimata group. And this means that when I create my slopes, these materials will come in and the layers will be as I want them to be. So now I'm going to create a new slope. This is going to be a 3D slope to begin with. And I'm going to use the boundary line as the basal surface failure definition. And I'm going to choose the top of sand as my basal layer. So here you have to set up your boundary line with the crest and toe dip and the sliding direction. So I'm putting in the relevant degrees for this slope. And I'm not using load cases, but you can add those in here as well. And you can add in slope clipping if you want. I'm going to leave this on none right now. And so with that, just check all the other properties. And if you're happy, press OK. And this generates the 3D surface. So if you see, I can rotate it around and it's got the layers in there. You can see that phreatic surface that I added in and the layers of the different material properties are in there as well. So now I'm just going to double check all the slope properties and make sure there's nothing else I want to add. This is good practice to make sure that the results you get are what you're after. If I switch to the analysis tab, I can increase the number of columns and this will increase the resolution. Once you've done this, you just need to press apply so it can change the visualization. As you can see, it's a lot more detailed now. And in the materials, I'll just change this from one material to layers. And that will mean that the layers we set up earlier with the uncemmented sand and the wetter matter group are then applied to the 3D slope scenario. And it's not just the same layer. So after you're happy, you can press the solve button and this then almost immediately calculates the factor of safety and the degrees in which it is potentially going to fail at. As you can see, this is 1.75, so fairly stable in a 3D slope scenario. But let's check the 2D slope and see what difference that makes. So for the 2D slope, I'm going to select the cross-section. As it's the only one, it auto-populated. I'm going to add in my phreatic surface, and I'm going to check all the other properties. Here I actually didn't define the basal surface as clip by layer, but as you can see, I'll go in and change that in a minute. So the first thing I'm going to do is reset the slope boundaries, the limits, and this is just so that it can calculate the failure based on these limits rather than just going and computing it across the whole area. It gives it more bounds, and we know that the slope is going to fail within this kind of threshold. So here I'm also resetting the min and max Z because it will make it visually nicer to just clip it down. And I'm going to change the failure surface to clip by layer. Again, you can do this in the setup. I just didn't in this scenario to show what you do if you forget. So here I'm selecting the basal sand because I think if it's going to fail somewhere, it's going to fail across that base of the sand where it's uncemented. And then I'm just going to check all my other properties, go to the analysis and change the corridor width. This allows me to then see the drill holes that I have in the spatial context. And that can be quite helpful if you've got kind of intersects with the different geological boundaries. I'm going to make sure that the materials are as they should be. And I'm just going to check the details one more time and press solve. So here I've been given a warning message about slopes, and you'll see also that I've got a massive dip in this line, and the factor of safety is reasonable at 1.32. To eliminate that kind of massive drop-off, we can add a tension crack at depth, and this should improve the results. So I'm going to do one at 4 meters and see what difference that makes. And I'm also going to reset the slope limits to see if that improves the warning message we were getting about non-continuous slopes. So here it's running again, and we'll see what results we get from it. So this failure profile looks a lot better with the tension crack in place. The factor of safety is still very similar at 1.31. And that's all there is to it. I hope you found that helpful. And if you have any questions, please reach out to support@tagsoft.com. Thanks for watching.